Good morning and welcome to this Friday's Cosmic Conversation here on the Morrison Planetarium Facebook Live stream, as well as on our OpenSpace YouTube channel. My name is Ryan Wyatt. I'm Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and I'm delighted to be joined today by Josh Roberts, who heads up our presenter team, and Dan Tell, who heads up the engineering team for the planetarium, both of whom are OpenSpace experts. And if you ever watched our streams, you'll know that we use this open source software that's being developed in part by NASA and other collaborators to open up a three-dimensional universe to anyone who wants to download it and fiddle around with it. We've been using that for a lot of programs over the last year as we've learned how to stream content. And we can run this in our planetarium dome as well, but I'd say that the past year, for me personally, has given an opportunity to learn a lot more about the software. So we're going to kind of just geek out today about some things that we enjoy about OpenSpace, or our favorite things to explore using the software. And that will touch on things here on Earth, as well as objects in our solar system and beyond. So I think we're going to start out with Josh sharing some of his favorite spots.
Certainly. So I love exploring Earth in a lot of different ways. My weekly show takes us so that we get to fly all over the solar system, but we all grew up on Earth, theoretically, for the people who are tuning in. So maybe you know Earth. It seems old hat, but there are so many cool things to see in satellite photography. I wanted to take you to some of my absolute favorites. So I am a medieval and early European history geek, and one of the things I think is coolest is the fact that you have on the coast of England a whole bunch of chalk deposits. And long ago, people figured out that if you scratch the ground deep enough, you can lay bare this chalk and you get this brilliant white, super visible layer that immediately pops out of the ground around you. So people have been inscribing these hill figures for a really long time. So this is one of the very oldest ones. Over in a hill on the side of a town called Uffington is a famous figure called the Uffington White Horse. So the fact that the history of this thing really extends back a tremendous distance in time to the early life forms that died to form the chalk, all the way to when human beings inscribed this figure, is just a really cool thing. And the fact that we can use space-age technology to image this and our amazing computer-age computers to see it at your home, I think is just absolutely fascinating. So there are tons of...
I just think of like the XTC album when I see this. I don't know if that's my question.
There's a lot of New Age jewelry you'll find online if you spend time searching for it.
I will say English Settlement is an awesome album if anyone decides that they want to go out and explore a great British band.
XTC?
XTC. Oh, I actually surprised you with that one. Sorry. I
feel like, considering like where Josh and my music tastes overlap, you'd think it would be in your catalog.
Yes. A quirky early 80s album, I think 1982, maybe 1983. It's called English Settlement. Has some of the best XTC, the three letters X, T, and C songs on it.
Well,
I mean, Black Sea is pretty good too, but English Settlement has the chalk horse on it.
I'm underexposed, so I'll have to check that out. You can actually see an early settlement off in the distance. There's a hill fort up on the side you can pick out. That kind of irregular shape, which, again, just super cool.
I think something as you're like, coming in and out too is like, this is, real satellite data. Like, we are loading it live. And if you download and play with OpenSpace, you get the same. And you might notice, we kind of went through this like layer of clouds. When you pull out far enough in OpenSpace, you're getting the actual like live satellite data from yesterday. We have a satellite called Suomi MPP, which orbits the Earth, takes a picture under its path every 90 minutes. And so you're looking at actual like the live cloud patterns that was Earth yesterday. You can even like look at today's Earth, but it's incomplete if it's still doing its orbits.
We get a lot of strips missing when we do that if we haven't given ourselves a sufficiently late time of day. So Clarissa asked, can the OpenSpace software see things like the Hubble photographs, like nebulas, Eagle Nebula? It's really good for mapping data. For showing an image, I would say that it would be a little bit more challenging. It can show pictures for sure, but we can actually do more three-dimensional representations of stuff like the nebulas Hubble takes a photo of. So this next one is one of my favorites because it features prominently Neil Gaiman mythology. But if you look down here, you can actually see inscribed on the side of the hill, if I get to just the right distance away, I'm going to try and draw on OpenSpace itself. One long stick here, one long stick here, and a humanoid figure standing between them. That is the Long Man of Wilmington. So another really cool hill figure, and one that kind of gives you that elongated perspective. So I think from the valley, it looks a little cooler than it does from the hill. And again, using OpenSpace, you get this actual topography, so you can see what it looks like from the valley versus from above. Okay, so a big zoom back. It's not just human-made stuff that you can see in this satellite imagery. I wanted to take a moment to visit the tremendous efforts that have been done by a non-human species. Way over here, we're going to fly across the planet over to Brazil.
And actually, while we're doing that, you might want to just answer the question that someone posed was, what's our favorite cosmic music of choice? I mean, we can probably each answer this as we take turns piloting, but I'll just plant that seed there, Josh.
Well, I'm going to confess that I'd never heard of them before Ryan stuck the CD in the dome, but there's a band called Mogwai, and they've got a really fun album, sans lyrics, that when you turn it on and you're about 100 light years away from Earth and you just zoom around, it is wonderfully atmospheric. But there's a lot of planetarium music out there.
I feel compelled to note that Mogwai does have some surprises, though. If you start to play this nice, quiet, restful music, suddenly you'll be hit by a barrage of guitar that might startle you. As one of my friends put it, half of their music sounds like something that his grandmother would enjoy, and the other half would probably give her a heart attack. But
So I'll leave it to our other pilots when they take over to give us their musical preferences. But I wanted to dive in here real fast. This is right at the edge of our data. So if I get too close, it'll disappear into a sea of gray rectangles. But this is a shot in a highly deforested area in Brazil, where you can see humankind butting up against the rainforest. And something that was discovered by people moving through this area, the locals kind of, I think, are used to them, so they didn't notice them as much. But there's massive mounds of dirt at fairly regular intervals all over the place. And if you look around here, you can actually see this kind of speckledy pattern in a lot of the soil areas as opposed to the trees. They are under the trees, but we can't quite see them because the trees block our view. But if you look around here, that mottled coloration in the gray and brown, those are waste mounds from termites, so places where termites have pushed dirt up onto the surface. And even though I can't show you an individual mound, you can look them up online, look for Brazilian termite mounds, and they are plentiful. What I can show you is the extent of how far these termites have gone. It turns out that if I look at the area where these termites are dominant, where they've made their influence known, it covers a huge region around here. You'll find almost identical mounds covering an area about the size of the US state Oregon or of Britain. So I thought that was just absolutely fascinating. And the fact that we can see it inside this imagery makes it really cool. So Clarissa's asking, can you see the Nazca lines? You can. We actually did a show in our dome where we got to fly to a lot of the great geoglyph art here on planet Earth. And there are tons. I live next to one in South City. But humans love drawing giant things on hills. It's something kind of fundamental. So Dan, where should we head next?
Yeah, so let's start heading towards the moon. So yeah, we're going to take a step away from Earth, head to our nearest cosmic neighbor. As Josh is sort of setting up that scene in flying, I'll throw in a cosmic music option. I just ran over to the record show while he was doing that. Yeah, I'm not like a big like ambient space fan, although I am wearing a Cats on Synthesizers in Space shirt. Yeah, I'm going to throw in a favorite cosmic music. This is a group called Casket Girls out of Atlanta. This is their album, True Love Kills the Fairy Tale. It's lyrical, but yeah, they do like a really cool, dark, ambient, spacey thing and have a lot of like space references in the music. So, you know, it's not necessarily like ambient planetarium background soundtrack, but it is like a cool, like heavy in its way album. So yeah, as we head into the moon, part of what I love about OpenSpace is the access it gives us to really amazing high detail NASA data. And there's been certainly in my career as a planetarian over the last 20 years or so, this really like amazing revolution in our understanding of astronomy. And it's sort of comparable to what the Voyager missions were 50 years ago now, of transforming our understanding and appreciation of space. So, you know, before the Voyager missions, we only knew of the planets through what we could see through telescopes. Those were the first chances to see these planets with up-close pictures. It was what revealed the nature of the outer planets to us. It's what revealed their moons to us. We knew they had moons. We didn't know what their moons were like before then. And then, of course, in the last 20 years, we've been sending these in-depth orbital missions to planets and bodies, including our own moon, that have given us such a vastly increased perspective on them. They've gone from being just the telescopic vision to becoming these complete fleshed out worlds that we have mapped in incredibly high detail. And so that includes the moon. For about 15 years now, we've had a mission going around the moon called the Lunar Reconnaissance Orbiter, which has been taking super high-res photographs of the entire surface of the moon. And as we drop down here, we're going to drop down into the Apollo 17 landing site. And one thing, if you can stop here, Josh, I want to point out. So Apollo 17 was the last mission that actually landed on the moon. Last time humans visited the moon was that 1973. And, you know, before we arrived on the moon, we didn't know quite what to expect. In fact, a lot of astronomers and geologists thinking about what the moon was going to be like expected the moon was going to be covered, because of its low gravity and lack of atmosphere, in like these giant steep cliffs and like towering spires of mountains, because in the low gravity, mountains could be steeper and they wouldn't collapse, and there was no wind or erosion to knock them down. But as we come down onto the moon, you might notice there's much more of this gentle rolling landscape. And that's because, as we realized when we got there, the moon is sort of flattened. Even though it has been weathered by wind or rain or water like on Earth, it's been flattened by meteor impacts. So the moon has been so pulverized by meteors that everything's been rounded off kind of gently, and it's covered with a 6-inch layer of superfine powdery dust that we call regolith. In fact, if you like listen to the Apollo 11 landing, like, you know, when they're like on the ladder of the LEM, Neil is like, it's like covered in a fine powdery substance. This was a surprise as we explored the moon. Anyway, dropping in here to Apollo 17. So the cameras on LRO are so good that as it orbits the moon, it's able to get these high detail pictures of the landing sites. And we can actually see, and we've got some labels here to mark it out, we can see the footprints and tracks of the astronauts from where they walked around the lander, where they drove the rover around. And right in the middle, there's what on the image shows up as just kind of a white spot of the remains of the lander. But if we zoom down, we have a little 3D model of the lunar lander as it would appear on the lunar surface. Of course, the upper half in reality has blasted back up into space. But you can see in the photograph below the remains of the lander still there on the moon as we left it almost 50 years ago. Now, what's cool about Apollo 17 is this was the longest time one of our missions spent on the moon. They were driving all over the place, and they drove up to the north of this area. And so, Josh, you want to target the boulder. And one thing sort of to mention, too, as I was sort of talking about this geography of the moon, or geology, you know, in planetarium and space stuff, like they took really nice pictures here at Apollo 17's landing site. And so this scene of like the mountains surrounding it, it's been very commonly used in planetarium shows to depict the moon. And like I said, you know, having worked with this for years, I was like, oh yeah, these are like these gentle rolling hills around the landing site. And it was really through OpenSpace, through this direct experience with the data, that I was like, oh wait, these aren't like gentle rolling hills, they are mountains. But in the photographs, there's no atmosphere on the moon. We don't have the typical depth cueing that we have here on Earth. And so the mountains look like up close hills when they're really like these giant mountains many miles away. So coming up here, this is one of the sites they drove to with the rover. And you can sort of see there is this trail running down this hillside, this like landside trail, and at the bottom of which is this big rock. And so this is kind of an example of getting to study different parts of the moon. So basically this rock that rolled down from the highlands here into this lower land region. And what's interesting is the moon is sort of made of two different kinds of rock. The lowlands are made of basalt, which is sort of your typical cooled down lava. But the highlands of the moon are made of anorthosite, which is a rock we don't have a lot of here on Earth. But anorthosite is basically slowly cooled down rock from the initial molten phase of a body. And so this is sort of like one of those like ancient pieces of the solar system. This is a part of the moon from when the moon still formed that, other than tumbling down a hill, is still basically untouched. And something that's been done by the OpenSpace team is taking all the photographs that Gene Cernan and Harrison Schmitt took on the moon, combining them together, through sophisticated 3D computer algorithms to reconstruct the actual shape of the rock from the pictures. And so this is what I think is really amazing. Is like the moon, you can go out, you can look at it with your eyes, with the binoculars or with a telescope, and see it as this orb in the sky. But using OpenSpace, you can turn it into a place that you can visit on a human scale. And in fact, if you were to carefully explore and sneak around enough, you can actually see a boot print in the dust near one of those rocks. But it's a little hard to find. I'm not going to make Josh do that. But,
Appreciate it.
Cool too that like just in sort of telling this story, I mean, if you kind of look at all of the different types of imagery and data that were layered in to tell that story is kind of fascinating, because as we zoomed in, you can see there was some photographs that were actually scanned from NASA archives and showing like, outlines and annotations on the surface, as well as this topography from the satellite missions, as well as the photogrammetry, like Dan mentioned, wrapping multiple images using multiple images to create a 3D surface and that. And it's kind of cool that we can bring all of these pieces together to tell this story.
Yeah. And so to further expand on that, let's back up and fly to the other world we have mapped super well, Mars. We do a lot of like work with our marine biologists at the Academy, and one thing they always are like is, we have Mars better mapped than the bottom of the ocean, which is actually very true. We have Mars mapped in really like shockingly amazing detail for being a whole other planet. And Mars, I mean, Ryan will often say in his shows, Mars is sort of the overrated planet. But I think Mars, like for me, it's always had this romance. I mean, I grew up in this time when we still believed that we were going to be living on Mars by now, or someone was going to be living on Mars by now. And I've always been a fan of old Martian fiction when we sort of believed that, or people hoped this was a world with living inhabitants. And, to drop in another media reference, I've sort of come to think of Mars as being like our fantastic planet. It is the planet where our imaginations have traveled to create this place where they commune with our visions of alien life, and just the difference between humanity and the cosmos is sort of all intersected on Mars. And so even though Mars might not be this romantic vision that we had in the past, what we understand of Mars today is incredibly dramatic and detailed. And so if we turn on the CTX layer, this is data that comes from the Mars Reconnaissance Orbiter satellite, much like that Lunar Reconnaissance Orbiter, which has mapped Mars in incredible detail. We have Mars mapped to about 6-foot resolution across the entire planet, and down to foot resolution in many other places. Not to mention, of course, we have a whole host of rovers driving around, including the recently landed Perseverance. And so if we just zip down onto the surface somewhere, this data, of course, is not just high resolution in imagery, but it's also high resolution in terrain detail. And so you can, we might not be living on Mars, unfortunately, and in our lifetime, I'm not expecting to visit Mars in person anytime in my lifetime for sure. But OpenSpace is a way to sort of relive this dream, relive this imagination, take yourself to Mars, again, in realistic detail, in human scale detail. We have patches from these cameras where you can drop down and basically stand in a boulder field where the boulders are the size of you. So once again, it's taking these things that a century ago were just dots of light in a telescope, that a few decades ago we had pictures of from orbiters, to now we have these highly detailed terrain pictures and terrain topography maps where you can insert yourself into the Martian landscape. And just like visiting a national park, you can experience the grandeur of this incredible dynamic world yourself through the software, and make Mars into a real place that you can visit. And that's what I think is the incredible power of OpenSpace is, this technology is not limited to us at the planetarium. You can do this yourself at home. I really love this part of exploring space. And so we can head away from Mars now. And let's visit one more destination in the solar system where, again, we have surprising amounts of data about what this world is like as a place we can visit. We're going to head all the way out to the edge of our solar system. And Josh is going to file this there. Of course, the solar system is mostly empty space. And if we don't have orbit lines on, you don't get this sensation. That's what it's like. Traveling through space. Space is empty. But yeah, here at the edge of our solar system, we're going to arrive at the dwarf planet Pluto. And Pluto is another case where up until 5 years ago, we didn't really know what Pluto looked like. If you've ever seen Pluto art in an old planetarium show, it's all, well, usually we would take like a picture of some other planet and just change the color of it. But yeah, 5 years ago when the New Horizons mission flew by, abruptly we got this whole new vision of Pluto. We discovered this whole new world. We had this amazement of like, whoa, there's like this heart on it. And Pluto is this incredibly dramatic place, it turns out. I've heard the New Horizons scientists say, going to Pluto, we expected to find high school level geology. Instead, we found postdoctorate chemistry, because it is a world governed by chemistry and temperature and this totally different environment than we have on Earth. So we're coming over this chaos terrain of the mountains to the east of Sputnik Planum, which is Pluto's heart. And especially we fly over the heart. Pluto, we know, is mostly made of different kinds of ices. There's probably a rocky core down in the middle, but it's mostly ices, particularly water ice and nitrogen. And so Pluto has a very thin nitrogen atmosphere, we now know. And, you know, Pluto was actually at its closest to the sun during the 1990s, and it's been moving slowly further away from the sun since then on its elliptical, elongated orbit. So as it's moving away from the sun, it's getting colder and colder on Pluto. And so this thin nitrogen atmosphere is condensing onto the surface. It's turning from gas and snowing down into ices on the surface. And so we think this area, Sputnik Planum, which you can see down below us, this is all basically a cap of nitrogen ice. And Mike Brown, who goes by the appellation of Pluto Killer, I think put this really well of, this is Pluto's ice cap, just like we have an ice cap of water ice on Earth at the North and South Pole. This is an ice cap of nitrogen ice, but it's because Pluto is flipped over almost completely on its side, just like Uranus is. This ice cap happens to be on Pluto's side, on the equator, because it's sideways. Now, what's kind of cool about this too is nitrogen ice, although a solid, doesn't have the same consistency as water ice. It's more like the thickness of toothpaste. So it's still like a little bit gelatinous. And we can see in the smoothness, there are these like hexagonal patterns, which if you've ever like taken a cup of hot coffee and like dumped some cold cream in there and watched, you might notice these like hexagonal convection cells of cream rising up as it warms in the coffee. That's what we think is happening here on Pluto. We think Pluto has some internal heating, either through the gravitational interaction with Charon or the decay of radioactive elements, which is keeping the planet slightly warmer near the core, causing a convection of this toothpaste-thick nitrogen, forming these hexagonal patterns. And then mixed in with that, if you look at the mountains off at the side, these are water ice mountains. And Pluto is so cold that water ice is as hard as granite. So this incredible contrasting landscape of these rock-hard water ice mountains sitting in this sea of soft toothpaste frozen nitrogen. And then combined with that, we've also seen evidence of what we call cryovolcanoes or geysers, where water and ice are spewing out of the inside of the planet, adding new fresh layers of water onto the surface. We've learned so much about Pluto from this mission. We have so much incredible data, and you can explore it yourself in OpenSpace.
So Dan, can you tell us your feelings then? Go
ahead. My feelings... yeah, I feel like I've gotten this from the horse's mouth on both sides. You know, we've worked with Mike Brown at the Academy. We've worked with Alan Stern of the New Horizons mission. You know, I'm the planetarium engineer. I'm not the scientist, but I think I'm very much in favor that Pluto is not a planet. And I think part of this, I don't know if we have the Kuiper belt loaded, but I think part of this really is there is a difference in how the planet's formed versus how these other objects are sort of left behind. I think dwarf planet probably wasn't the best name they could have chosen. And I remember someone else around time making a better case of like, we should have called these things planetesimals, because that's really what they are. They are still the leftover chunks of what would have become a planet that just didn't become a planet. And that's what I think is really important about the definition of planet versus dwarf planet is it is showing this example of like something different happened with the planets. They really did vacuum up most of the other stuff in their orbit, added it to their own mass, and became these larger, I mean, the largest dwarf planet and the smallest planet are separated by about 5 orders of magnitude. They really did become these larger objects that have a greater influence on their part of space versus objects like Pluto, which are clearly sort of these chunks that didn't form all the way into one of these major planets. And it's not to say Pluto's any less. Pluto is teaching us this incredible amount about this huge, diverse population of bodies out in the outer part of the solar system. But I think it is right to recognize that something different happened between these bodies. They're still worlds. They still have incredible geology. But this formation process, it makes sense to differentiate what was happening there, I think.
So Dan and Ryan, what are your favorite moons this week?
Since we were just at Pluto, I would say a favorite moon is absolutely Triton going around Neptune. And what's cool about that is just talking about these Kuiper Belt objects. Triton, basically, we believe was a Kuiper Belt object that was captured into orbit around Neptune. It is the largest moon that sort of orbits the planet in the wrong way. And especially now that we have these great pictures of Pluto, we have some actually pretty good imagery of Triton from when the Voyager mission flew by. And we can actually see there's a lot in common between them. We know that Triton has nitrogen geysers on its surface. It has this nitrogen ice cap on its south pole. And it's this great example of, like, you know, had Triton not been captured into Neptune's orbit, Triton would be the biggest Kuiper Belt object instead of Pluto.
Right.
Yeah, and it's just this cool thing of, like, now we understand these are super similar objects in this similar part of the solar system that have more mysteries to be unveiled to us if we can explore them more in the future.
Well, I think the other, since I guess I get to chime in as well, one of the other moons that I think is just fantastic is Enceladus, a moon of Saturn, that I think Josh has at some point visited in the tour that he does on Wednesdays. That's just so exciting because that you look at that moon from a distance, and it's just sort of this you think kind of featureless white, kind of uninteresting place, and yet as various spacecraft explored it, but particularly Cassini, discovering that it has a subsurface ocean, like a couple other moons in our solar system, but actually has a lot of really potentially interesting chemistry going on that could be related to life underneath the icy surface of the moon, out of the distance of Saturn, which is of course much farther from the sun than Earth, and just the idea that it was a surprise, but also then that the Cassini mission was able to make changes to its flight plan to go and take a closer look, to plan out orbits that would take it a little closer to Enceladus, so that it could actually fly through, for example, geysers that are coming out of the south pole of Enceladus. And so I think Enceladus is probably my favorite, at least today. So.
And you can get an up-close look at it in our planetarium when we reopen and premiere our new show later this year.
Ooh.
Very good. Yes, good plug, Dan, because in fact, we're paying a very close visit to Enceladus in our show. And we just had one other question for Naomi about our favorite applications for OpenSpace, flybys, presentation, and so on. First of all, there's a ton of great videos of people using OpenSpace to present content, and we're trying to show some of the things that we just like to talk about and also kind of like to explore using the software during today's program. But I will say, like, one of my personal favorites is if you get to watch, and I think there are some videos online. We did a cosmic conversation with her a while back, but Jackie Faraday, who's a researcher at the American Museum of Natural History, talking about how OpenSpace has allowed her to look for patterns in Gaia, and she, as a scientist, is able to use the software to do data exploration, which I think is pretty fun, fantastic.
I would love to jump in. Go ahead, Dan.
I think one of my favorite strengths is the data in OpenSpace is so good. We have such good parity between the positions and the satellite data that, like, you can use it to really recreate the experience of exploring the solar system. You know, you can follow along with a mission like New Horizons or Voyager or the Apollo missions and really see what the spacecraft or the astronauts were seeing during this experience. So really, really bringing that experience of space to yourself.
And actually, we had a conversation with one of the programmers for OpenSpace earlier this week, and he said that when he sees an image from, for example, Perseverance, he'll go down and try to recreate the actual image in the software, which is pretty cool to think about being able to do that.
I would say my absolute favorite application for OpenSpace is when we have an open museum floor. You can plug in an Xbox controller and hand it to a guest, and they get to fly around and explore whatever place in the solar system they want, and we get to stand there and just tell them cool facts about it. And that has been an absolute hoot.
Yeah, that is all very, very cool. And being able to share these kinds of experiences is fantastic, because I think, as Josh or Dan both mentioned, once upon a time, the software that we needed to do this in the planetarium was not something we could just share with people. And now we can. So I'm going to wrap up kind of our trio of sort of mini presentations by taking us outside the solar system. And to do that, I'm starting with our view of the solar system here the orbits of the 8 planets. Yeah, sorry, Pluto, we already covered that territory, but also the trajectories of some of the 5 fastest spacecraft. And I think one of the things that is always like blown my mind about astronomy is that we've learned so much about the universe around us, not by visiting places, although trips to Mars and the moon and Pluto are all phenomenal ways to get information about these objects that are relatively close by. But we've actually figured so much out by observing just light from other objects. And so when you look at the stars that are kind of drifting by in the background there, those are observed stars. You can go out and look at them on a clear night from here on Earth. But as we pull away, we're going to see that we're actually seeing them in 3 dimensions, and that the constellation patterns that might be familiar are rapidly something that kind of go away and disintegrate. Oh, thanks. We shared that link to the Cosmic Conversation with Jackie Faraday there. Again, I would recommend it. Of course, I was in conversation with her, so that might bias my opinion somewhat. But actually, let me bring up those constellation outlines. If actually, to do that, I think you need to use the interface. We often try to kind of gloss over this, but as Josh said, one of the great things is being able to hand a controller to someone and allow people to play. And you can do this at home if you download OpenSpace, and we'll share that link in the chat comments and that. But I'm actually going to turn on the constellation outlines here so that we can talk a little bit about those. And to do that, I'm just using a menu here that's called Scene so that I can pull up constellations, and I happen to know that that's the right button for them. So I'm just going to now hide that. But if you happen to recognize your constellations from Earth, right now you can see the large and small Magellanic Clouds, which is a pretty clear indication that we are down in the southern hemisphere. There's the Southern Cross, Alpha and Beta Centauri, part of the Centaurus, the constellation, drifting by here so that we're seeing the center of our galaxy, and Scorpius kind of disappearing off the bottom of the screen there. We're seeing Aquila, the eagle, Lyra, the lyre or harp, and these are all, if you're and actually here Cygnus the swan up here toward the middle of the image. Now those are all familiar constellations, but one of the things I think is really cool to do is just, and let me go ahead and kind of put the pedal to the metal here and pull back from our view at the solar system. And pulling back here, we have some color coding on the constellation outlines. The blue constellations are the kind of very familiar constellations, Orion and the Big Dipper. The red constellations are the constellations of the zodiac, which could lead me down a dreadful digression, but I won't do that. But what's cool is just by pulling, we probably pulled maybe a few tens of light years away from Earth here. And what we're seeing is that these constellation outlines, which draw pictures that basically connect the dots from on Earth, turn into this, what I like to call like a pincushion, where everything is sort of pointing back toward Earth. And the only reason it's doing that is because stars are, in fact, at different distances. And as we've measured the distances to stars and put them into this coherent catalog, we've been able to construct, again, only by studying the light from the stars, we've been able to construct a 3-dimensional atlas of the universe. And that's so much of what is kind of part of the OpenSpace story, is being able to create a visualization platform to kind of look at and share these data. And one of the other things that's cool too, and again, you can do this if you download the software and start playing with it. I don't know how clear it is on the screen, but just like pins have that kind of big knobby thing at the end, or maybe a small like disc, because when you draw pictures of in the sky and play connect the dots, you're going to use stars that are relatively bright as seen from Earth. Now, some of those are bright because maybe they're not intrinsically very bright, but they're close to us. Others are bright because they are intrinsically bright and they could be very far away. And so because this pincushion, this connect the dots, is showing you stars that are both close by and maybe not particularly bright and far away, but if they're far away, they are almost certainly quite intrinsically bright. If you look at the tips of the most, and it's a little hard to see here on the screen, but if you look at the tips of the pins in this metaphorical pincushion, you'll notice that they're brighter, because the brighter stars, the intrinsically bright stars, are preferentially the ones that are located farther away. So I just think that's a kind of cool aspect of the digital universe model in general, and of course, OpenSpace can give you a chance to see that. But I want to, in just a few minutes we have left, kind of pull us way out and highlight just a couple of things that I also like about the atlas. Now, unfortunately, the way it works on your streaming Facebook or YouTube, you probably couldn't see many stars flying by as we left the Milky Way galaxy. But one of the most beautiful parts of the OpenSpace software is, in fact, this representation of our Milky Way. Now, I showed you the distance that those five fastest spacecraft had traveled in the solar system, and none of them had traveled nearly far enough out to get a look at the Milky Way galaxy. Instead, we figured out, using data like the star positions, but also for objects that are much farther away but easier to see at great distances, we figured out the structure of our Milky Way galaxy, but figuring out how to illustrate that can be challenging. And what the team that's assembled the OpenSpace database has done is they've combined observational data of what we know to be objects that are in the galaxy in their three-dimensional locations with a computational model that is a three-dimensional model of a galaxy that basically is constrained by those observations to create what is really one of the most beautiful 3D models, I think, of our galaxy. But I have this problem that whenever I start to get this far out, I want to go like all the way out. So just very quickly, I want to point out something else you can do in OpenSpace and sort of the capstone to kind of these conversations about looking at the universe around us and how vast it is. And that is that we're now fading up some of the locations of galaxies. So we left our own home Milky Way galaxy with that beautiful representation I described. But now seeing the locations of other galaxies, all of these, again, kind of accurately measured. I'm really going to kind of speed up to go out to showcase some of the surveys of galaxies even farther from home. Again, each one of these individual points isn't a star. It's a whole galaxy, which may contain hundreds of billions of stars. And although it looks like the galaxy is sort of hourglass shaped, or at least very, shall we say, non-uniform, to use a kind of more astronomy physics-y term. In fact, the regions that happen to be densely populated with galaxies are just ones that happen to be surveyed better. And so instead, what we're seeing here is not that the universe is shaped like an hourglass, but just that like these dark regions here are regions that haven't been explored well. But what I wanted to point out is this punchline when we get all the way out to the edge of the observable universe, which is the way we illustrate the cosmic microwave background. And normally kind of set this up a little bit more, but basically as we've been traveling farther from home and past these objects whose distances have been accurately measured, we're not only looking out into space, we're looking back into time. As I mentioned at the very beginning of my section, when we're looking out at these objects, we're studying them using light, but light travels at a finite speed, 186,000 miles per second, pretty fast, but still a finite speed. So 186,000 miles per second, 300,000 kilometers per second. That still means as we look out into space, we're observing objects whose light has taken time to reach us. And the punchline to this is this baby picture of the universe, the cosmic microwave background. And here, if you're familiar with the WMAP or Planck imagery of the cosmic microwave background, you might be used to a more colorful kind of representation. But we've sort of tried to simplify it in our representation here. And the modeled image of the cosmic microwave background is shown with bright spots, which are basically hot parts of the early universe, and dark spots, which are basically cool parts. And those tiny fluctuations in the temperature of the early universe correspond to tiny fluctuations in density, and those evolved into the clusters of galaxies and some of the stuff we zipped by very rapidly closer to home. And so this is really one of my favorite things in OpenSpace, is to be able to see this kind of really big picture of our universe, how much we've been able to map in terms of distances to galaxies and other objects, even objects in our own galaxy, and how that sort of gives us a very humbling perspective on our own home planet and our position kind of deceptively in the middle of this giant model, not because we're at the center of the universe, but because we're the ones drawing the map. So that's kind of what I like to think about and play with in the OpenSpace. platform.
And if I can add a little favorite about the CMB too, is, we chose that orange color for it because although it is now microwave light, at the time it was emitted when the universe was a mere 380,000 years old, it was visible light. It was in the visible range. The universe was as hot as a star, and it was as hot as a star that was about 4,000 degrees, and it would have been that color. It would have, of course, been so bright, it would have oversaturated rods, and also you would have been in a hot plasma and incinerated. But if you could somehow been there and seen it, it would have been this very flat, even orange light everywhere. And so that's what we're trying to represent with that color scheme of we are exaggerating the differences of temperature in that light, but the universe was orange at one time and has now been stretched out into microwave wavelengths. In fact, we live at a very fortunate time because that light will keep stretching out and eventually become invisible to observers of the future.
So it's a very cool and humbling point to kind of sort of end the program with. But if you have any questions we are heading back toward Earth and toward our solar system. If you have any questions for me or Josh or Dan, please feel free to share them on YouTube or on Facebook, and we can do our best to try answering them. Otherwise, I'm going to interpret stunned silence.
We had one pop up for Dan, I think. Is there any atmosphere to speak of on Pluto?
Yes, so Pluto does have a very thin atmosphere, which seems to be mostly nitrogen. And so again, as I mentioned, Pluto was at its closest point to the sun from 1979 to 1999. In fact, during that period, it is closer to the sun than Neptune because their orbits cross, although they happen to cross in such a way that they never intersect, which is very important to why Pluto is not just part of Neptune. Presumably, Tritons did intersect Neptune at one time, which is why it was captured. And so, as Pluto is at the closest to the sun, it is warmer. And so seemingly these nitrogen ices on Pluto, sublime into nitrogen gas, which forms a thin atmosphere on the planet. And when New Horizons flew by, Pluto is getting colder and colder right now as it is on the 150-year journey to the furthest part of its orbit. And so as we are seeing basically fall on Pluto, we are seeing it getting colder day by day, and that nitrogen atmosphere itself condensing from a gaseous atmosphere into solid nitrogen. To drop another media reference, there's a Fritz Lieber story I really like about the Earth getting knocked away from the sun, where its atmosphere also progressively freezes, and so they have to dig through a layer of carbon dioxide and then nitrogen and then oxygen and bring in buckets of oxygen to melt over fires in sealed up apartment buildings to stay alive because as temperatures get colder, everything freezes. So
I feel melting oxygen over an open flame is a profoundly dangerous thing. But
plus incredible.
Desperate times, desperate measures, I guess, right?
Yep.
And on the topic of Pluto's atmosphere, though, I will note that when New Horizons flew by, it actually looked back at Pluto and imaged the atmosphere. You can actually see layers of the atmosphere in a kind of backlit image of Pluto that's pretty mind-boggling. I realized I didn't answer the question about music. So although Josh did mention Mogwai, which is one of my favorite bands, but I'm going to go pure classic. As the eldest member of the three people presenting here, I'll just go right for Brian Eno. And although we looked at the moon and went far beyond it, Apollo Atmospheres and Soundtracks is one of the most spectacular, not only soundtracks, but great ambient album. So we'll just go for a classic there from my recommendation.
I'll second that one too. That one's awesome.
And speaking of atmospheres,
go ahead. Atmospheres.
I was just gonna add, part of OpenSpace is still heavily under development, and part of what's being done right now is building up atmospheres on more planets. So you might have noticed as we flew into Mars, there's a simulation of Mars' atmosphere. We're simulating Earth's atmosphere. There's been work done on Venus's. We are building out Titan, Saturn's moon's atmosphere in the current build. And so optimistically, it might be cool if in a future build, we do have Pluto's atmosphere built up into OpenSpace as well. So I'm going to stay tuned for as the software continues to progress. And if you're a software developer, there might even be opportunities to volunteer for this project if you think it's really cool.
That's right. It is an OpenSpace is an open source project. So, yeah. Well, very good. I can't see if we have any additional questions, but
Naomi seconds that melting frozen O2 over a fire sounds like a dangerous idea, but a good way to stay warm very quickly and briefly.
Yes, Bucket Full of Air is the name of that story. If you if you want more details on it,
Is it Bucket Full of Air?
Bucket Full of Air.
All right.
Well, wonderful. Thank you both for your time. This has been a really fun presentation.
Yeah. Have to do it again sometime.
With that, thank you all for tuning in, and we will catch you next week. Have a great day.